So we're ready? Okay, so let's continue. So as Moritz said, I'm part of the virtual lecture, but I'm more involved in the organization of phase 3, so the workshop. And so today is a special day for this lecture because Alan McIntosh would have turned 82 today. Unfortunately, he died in 2016, but still, he was one of my collaborators, and I still have a strong feeling for him today. Okay, so what you saw last time is that that was an example of a divergence form operator for which the domain of L was not included not included in any H1 plus epsilon of Rn, right? So epsilon positive, right? So no way that the domain of L to the power alpha, if alpha was bigger than half, less than 1, say, is not included in H to alpha, right? So that's why the square root is exactly at the border of what is known, because what we know is that if alpha is between 0 and a half, it is always the case that this domain is H to alpha, right? Omega, or let's say Rn. So alpha equals a half is just the border case. And so L, there exists an example of L of divergence form for which we have that, right? So for that operator we have that, but we know that for any divergence form operator we have that. Okay. So alpha is equals a half is just the limiting case. And so we have, what we aim to do in this lecture is to prove this proposition. So if I'm not mistaken with the numbers, it's proposition 12.7. So assume that so V, as usual, H, V are Hilbert spaces. V is in H. A is a sesquilinear form. Which is coercive, is bounded. What else? And L is the associated operator. On H. So it means that so L goes from the domain, its domain, which contains V, which is contained in V, sorry, in H, and for all U in the domain of L, what we have is that LUV. So this is the scalar product on H is equal to AUV for all V in V. I hope it's, is it the first? Yeah, I think it's the correct setting. And so the proposition says that in this setting, the following are equivalent. So we have two assertions. The first one is that V is in the domain of square root of L, and we have this estimate for the square root of L applied to a function U. This is less than or equal the real part of A of U, and this is for all U in V. So this is equivalent to the second assertion, which is the square function estimate this following square function estimate holds for all U in V. So the square function estimate is it's integral from 0 to infinity of TL 1 plus T squared L inverse applied to U. So I take the norm of that squared dt over T, and this is less than or equal to, well, up to a constant, the real part of A of U, and this holds for every U in V. Okay. So these two, A and B, these two assertions are equivalent, and moreover, if we have either A or B satisfied by L and its adjoint L star, then we have so let me write it completely. Moreover, if L and L star both satisfy B or equivalently A, then the domain of the square root of L is equal to V, and this is also equal to the domain of the square root of L star. Okay, and we have the fact that the square root of LU squared is equivalent to the real part of A of U, and this is also equivalent to the square root of L star U squared for all U in V. Okay, so you're familiar with this. Equivalent means that you have an upper and lower bound up to constants. Okay, the constants could be different. Okay, so the goal of today is to prove that, right? So how do we prove that? So maybe just one remark about this this square function estimate. So if you replace L by a real number x, right? So for x strictly positive, if you try to compute tx divided by 1 plus t squared x dt over t, so it's an easy computation, right? So you just so the t here disappears. You you make the change of variable of s equals t times square root of x. Then you will have 0 to infinity. So there's a square root of x going with the ds. So you still have a square root of s. There's a ds 1 over 1 plus s squared, right? And this is so we know a primitive for this this function. It's arctangent, and plus infinity is pi over 2, and at 0 it's 0, so this is pi over 2 times square root of x. Okay? So the constant would be, the constant c is pi over 2. So of course the whole thing, so the square root of x, the whole thing, it would be to replace x by L, the operator, right? So you can do the same if you replace x by a complex number with a positive real part. Well, at least not on the negative real line, so that you can define the square root. Okay? Good. Maybe another remark. So that was the first one. And the second one is that compared to the square root estimates you already know, so the square root estimate, the square root function, the square function you already know is that for psi, a good function, okay, what you know is that u squared dt over t integral from 0 to infinity, right? The square function for a function psi applied to L would be this, but here it's not quite that, because we have a t squared. So how to go from one to the other? Well, you just if you make the change of variable t equals s squared, what you would get here is so what is the dt over t? This is 2 times ds over s, and so I hope I'm not mistaken. Right, so maybe maybe I write it the other way around. Okay, so ds over s is 2 times dt over t. So this one would be 2 or no 1 over 2. No, yeah, 1/2 integral from 0 to infinity of psi of SLU squared ds over s. Right? So that's just to show you that this, whether you have a t squared or a t, it's the same. Okay, so now the proof. So A implies B, right? So we assume that we have the first estimate, and we want to get to the square function estimate. Okay, so what can we write? So U is in the domain of square root of L. So what's in the integral? 1 plus t squared L inverse of U. This is what you write it like this. So this L, you split it in square root of L times square root of L. The square root commutes with the resolvent. So this would give 1 plus t squared L inverse square root of L U. So this is for all positive t. And this one, you write it as a f of t squared L applied to square root of L U, right? And f here is a good function, holomorphic function. It's exactly square root of z over 1 plus z. And this one is in the good space, right? It's in what is called h infinity 0 of s phi for all phi between 0 and pi, right? So this is phi, and here I have the function square root of z divided by 1 plus z. It's holomorphic, has the good properties. And then what we know is that for an operator of divergence form, we have the square function estimate. This was in a previous lecture. So the square function estimate says that integral from 0 to infinity f of TL of, let's say, v squared dt over t is bounded by up to a constant v squared, right? So you just instead of v, you write square root of L u, and you get that we have the integral from 0 to infinity. So f is, so that's this one. So we have TL1 plus t squared L inverse applied to u squared dt over t. This is then less than or equal to square root of L u squared well, actually it's equivalent. Sorry, I should have. It's equivalent. So I use only that one. And by A, what I know is that I think it's also up to a constant. Sorry, what I should have here, it's up to a constant, of course. So by A, this is less than or equal to A of u, right? No, sorry. What did I? Sorry. I'm completely mistaken. Where should I? Actually, that's that one that we need. This is less than or equal to that. And by A, that one is less than or equal. Sorry. The real part of A of u. Okay? Sorry about that. Okay, so it's exactly what B says. So B is proved, right? I started with u is in the domain of the square root of L, and I proved exactly what sorry, no, that's not. Is that? I wanted B for all u in V. V in the by the assumption A is in the domain of the square root of L, right? So that everything works, hopefully. Do you agree with all that? Yeah, I didn't forget anything else. Okay. So now, the other way around. So we first started with A implies B, so now why B implies A? So we assume that we have the square root estimate, and we want to show that V is in the domain of the square root, and we have the estimate as shown. All right, so that's maybe so first what we will prove is that this one is less than or equal to the real part of A of u, first for all u in the domain of L, right? So that's our first point. So, how do we prove that? First, for all V in H, we have a Calderon reproducing formula. Which implies that V is equal to a constant integral from 0 to infinity, and then we have SL to the power 3/2 1 plus SL to the power minus 3 V ds over S. So why is that? And what is this constant? It can be calculated. And actually, the constant satisfies this thing here. We have x to the power 3 let's say 3/2. Wait a minute. It seems that no, sorry. S. As before, 3/2 1 plus sx to the power 3 ds over s. That should be equal to 1 for all x. Let's say non-negative. So if x is equal to 1, I can write it like this. Sorry. Okay, and you could check that. Well, this is an integrable function, right? Because near 0, it behaves like a square root of s, which is integrable. And at infinity, it behaves like s to the power 4 minus 3/2, which is integrable as well at infinity. And actually, you can compute this constant c. I didn't. I just believe what my co-author said. Should be 8 over pi. So it means that this integral is equal to pi over 8. Okay. Good. So far, so good. So with this, the Calderon reproducing formula says that then we have that. And if you apply, so you change the variables, you put an s equals t squared. And for v, you use square root of L applied to u. And then what you get is that the square root of L u, using this, right? This is c times integral from 0 to infinity. So I put a square root of L, so here I have an L to the power 2, and S is t squared, so I have TL squared. Okay. I have a t. No, I have a, sorry. So, S is t squared. So I have t to the power 3. I have an L squared. sorry, I have a 1 plus t squared L to the power minus 1. V is square root of L, square root of Lu is already taken care of. And as before, ds over s is 2 dt over t. So I have a 2 in front, and here I have a dt over t, right? So this is just this formula applied to v equals square root of u, and making this change of variable s equal t squared. So now, if I take w in h, and I take the inner product of square root of Lu applied to W using this formula. So, okay, there's always this 2 times c in front. I have the integral from 0 to infinity. Then I have a, so maybe this t squared and this t, they disappear, right? So I have a t squared L squared 1 plus t squared L squared inverse u applied to W dt, right? I could have yeah, okay, maybe I keep it like that, sorry. So there's a t squared. And then I split that in two. There's something going in front of, there's a minus 3 here, sorry, nobody's reacting, but there's a minus 3, right? Forgot. So I take some of this one, put it on the other side so that I will get the adjoint of L, right? So to split it in a correct way, so I take here the absolute value. So this is 2c times, I have the integral from 0 to infinity. So what do I keep here? I keep an TL 1 plus t squared L. There's no squared here. To the minus 3, to the minus 1. U. So what is going on the other side? I have a t squared. I have 1 L star, and here I have a 1 plus t squared L star to the minus 2 W, right? Then a dt over t, and that's it. Good. So now I need space for continuing the calculation. Okay. Now, what happens with that? So, again, what we have is square root of L u applied to W. W is in H. This is 2c integral from 0 to infinity. I just write down the last line. TL 1 plus t squared L inverse applied to u. And then I have a t squared L star 1 plus t squared L star to the power minus 2 W dt over t. And then I use Cauchy-Schwarz. Okay. Cauchy-Schwarz. So for that, so here I have the function no, here. Here I have the function f. This is a z divided by 1 over z squared. This is also a good function, right? This function is also a good one. So what I have here is 2c times integral from 0 to infinity of TL1 plus t squared L inverse u squared dt over t to the power 1/2 times integral from 0 to infinity of f of t L star of w squared dt over t to the power 1/2. Okay? So this is Cauchy-Schwarz for the measure dt over t. Okay? So that one, by assumption B, which I unfortunately erased already, so I still have this 2c. That one is less than or equal to the real part of a of u to the power 1/2, because there's a power 1/2 here, right? So this is this estimate that from here to here I use my assumption B, okay? And here, by the square function estimate, this one is smaller than W, the norm of W, okay? This is from here to here, this is the square function estimate. Okay, so now what happens? Take now W to be square root of LU, and what you get is that we have here square root of LU squared is less than or equal to, well, this 2c I can forget, right? It comes in this tilde in the less than or equal, okay? Of the real part of a of u to the power 1/2 times square root of L u, right? So what we get is exactly what I announced, is that we have, well, I just put this square root of L. So square root of LU is less than or equal to the real part of a of u to the power 1/2, right? And this is true for all u in the domain of L. So this is exactly what E was. So E is proved. I is proved. Sorry. It's an I in English. Good. So now what we want to have is the same thing, but not with u in the domain of L, but u in the domain of the square root of L. Right? If I'm not, so where is it? For all u in V. So what we need is we need the same estimate for all u in V, and not only in the domain of L. Okay. So so this is the second point of the proof, right? So you just put, you take u in V, and you take a sequence uk in the domain of L, so that uk converges to u in V. So the convergence is in V. It means that the norm of uk minus u in V goes to 0. And what is this norm? The norm in V is the norm in H, plus the A uk minus u, so it's not exactly that one, but it's this norm in V. Okay? So it means in particular that uk converges to u in H. And so by what? What I know also is that square root of L uk minus square root of L uj by what we just proved, this is less than or equal to the real part of uk minus uj. This is by the point I, right? Because uk and uj are both in the domain of L, so I can apply what I just proved for all u in the domain of L. Real part of A of this. And this, as k and j goes to infinity, since we know that uk is convergent in V, it means that this goes to 0. Okay? So it means that the square root of L uk is a Cauchy sequence in H. So it converges to something in H. H is a Hilbert space. and the square root of L is a closed operator. So I say again, I have UK converges to U in H. I know also that the square root of L of UK converges to something in H, something I call, I don't know, V. L is a closed operator. It means that U is in the domain of the square root of L, and square root of L U is equal to V, or V is equal to the square root of L applied to U. Therefore, U is in the domain of the square root of L, and V is equal to the square root of L U. Comes from the fact that the square root of a divergence form operator is a closed operator in the Hilbert space. Okay. Okay, so what we get is that this one is also true for all U in the domain of L. We had since the square root of L applied to UK squared was less than or equal, and this constant is independent of almost everything, A of the real part of A UK. At the limit, just take k to infinity, what I get is that square root of L U squared is less than or equal with the same constant of the real part of A of U. Right? And that was for U in V. Right? So what we proved is that if U is in V, then U is in the domain of the square root, and we have this estimate. Okay? And now it remains to prove what I said at the beginning. So if we have A or B satisfied by both L and L star, then we have the square root property, the Kato square root property. So what we have proved so far is that A is equal to B. In the proposition there was a moreover part. And that is what I will show you in a moment. So it was the last part of the proof of the proposition is that if L and L star satisfy A or B, which are the same, then the domain of the square root of L is equal to V is equal to the domain of the square root of L star, and we have the equivalence of the norms. The square root of LU squared is the same as the real part of A of U, well, more or less, up to constants, right? And this is also equivalent to the square root of L star U squared. Okay? So, the only thing to show, we already know. So this is by the assumption by B, right? Sorry. No, by A. By A. That V is in the domain of square root of L, and also this is the assumption A for L, and we also have the assumption A for L star. But by symmetry, what we only have to do is that to show that the domain of square root of L is in V, to show that they have equality. Domain of square root of L is in V. And of course, by A as well. So we know that and real part of A of U is controlled by the square root of LU squared. Is that correct? Yes. And here we have also, and the other way around would be square root of LU squared controlled by the real part of A of U. No, the other way around. Sorry. Yeah, A is the other way around. So what we need to prove is the other direction, the other estimate. Okay. So we have to prove these two, and then by symmetry we do the same thing with L star instead of L, and then we're good, right? Because if L is a divergence form operator, L star is also everything which goes for L goes for L star. So first point, so what we know is that take first U is in the first U in the domain of L, and then what we have is that the real part of A of U, this is the real part of LU U, right? This is exactly, so without the real part, this is also true, but I only take the real part. And here I split my L with square root of L times square root of L, and I put a square root of L on the other side, which becomes then a square root of L star. So what I get is that I have here the real part of square root of L U square root of L star U. And this is less than or equal to square root of L U times square root of L star in norm U. Okay? But what I know is that this square root of L star U, so I also have that, right? So what I know is that that one is controlled by the real part of A of u to the power 1/2. Okay, so the whole thing here is controlled by square root of L u times the real part of A of u to the power 1/2. I put 1 on the other side, or so that at the end what I get is that the real part of A of u is controlled by the square root of Lu squared, which is exactly the other way around. So that one, so if I have, so I have that one and this second one, these two together give exactly what I wanted to have, is that the real part of A of u is equivalent to the square root of Lu squared. Okay? So this is all good for u in the domain of L. Okay? And now how do we conclude? Well, as before. So I can approximate a u in V. Right. No. U in the domain of square root of L. So what we know is that since A is elliptic, we know that the norm of u in V squared, well, I took it as a definition, but actually is less than or equal to the real part of A of u plus u in H squared, right? And since I have this, now I know that this is smaller than or equal to square root of L of u squared plus u squared. So this one was for u in the domain of L, but what we know is that the domain of L is a core for square root of L, right? It means that I can approximate everything in the domain of the square root of L by a sequence in the domain of L, and the sequence, everything converges correctly, right? Then so what we know here is now that so if you just forget about that for a minute, you just, well, maybe that one, you just put these two together. You use the fact that the domain of L is a core for square root of L, then you can conclude the domain of square root of L is in V, and what we just proved for u in the domain of L also applies for every u in the domain of the square root of L. So 12.6. So this well, that was maybe the orange one, right? This equation in orange. This holds for all u in the domain of the square root of L. Right? Do you need more explanation at that point? This is by density, right? So it's as before. You take a sequence uk in the domain of L, which converges to u in the domain of the square root of L, and so on. Okay. Good. And to finish it, there's a last corollary, and I will finish with that. Well, this finishes the proof, right, of the proposition. So proposition 12.7 is proved. So, as a corollary, so it's corollary 12.9. Did I forget 12.8? Oh, that was a remark, but so to establish the square root property for L or A. So to prove, so what is theorem 12.1 you saw last time? It is sufficient to prove well, necessary also, but it's what you will do in the next lectures, that integral from 0 to infinity of TL 1 plus t squared L inverse u squared dt over t. So this is in L2 of Rn. So now we are back to a divergence form. So L here is a minus div A grad. So you know that so it comes from the form AUV integral from so A grad U grad V on Rn, right? With A complex valued matrix which has good properties so that everything works, so coercive, bounded coefficients, and so on. So this is for U and V in H1. So H1 of Rn. So this is our our space V. H is L2. And what we want to prove is that this is, so this would be the square root of L U, and this is controlled by the gradient of U in L2 squared, controlled or equivalent, which is more or less the same, but yeah. Okay, so that's the whole point to prove the Kato square root property. So, well, you know maybe a little about the history about this result. It was proved first in dimension 1, also in any dimension if the matrix A was symmetric or real valued, but the proof for the whole for all cases, for complex valued matrices, it was proved in 2001 with McIntosh in the authors, but O'Share, Lacey, McIntosh, Chamichian, Hoffman. Well, it's the wrong order, but they are all there, I think. Okay, so that's next task to prove something like this. So for these operators, minus divergence A gradient, and well, in one of the projects you will be proposed will be the same thing but in domains, so with boundary conditions and so. But you have time to decide. I guess it's more or less what I wanted to say. Let's see. Yeah. So maybe you can also look for more details in the script, but I guess I will stop here. It's more than 1 hour. I think it's enough. If you have questions. No? Everything is clear? So maybe we can stop here.